In this project, we propose Swiper, a framework for lightweight air typing via image classification and image-to-sequence modeling. Over the course of this video, we will talk about the task of air typing, the data pipelines and datasets that we created, the model architectures that we developed, image classification and image-to-sequence, the results that we obtained, a demo of our system, and a discussion of our findings. Let's dive right in and talk about the task of air typing. Air typing is the process of capturing mid-air finger movements and converting them into text. It enables hands-free text input, which is something that has applications in accessibility, productivity, and potentially even the metaverse. You can think of air typing as being useful in a scenario where you wanted to enter text, but you could not use your hands to physically type and press keys on the keyboard. In this scenario, with air typing, all you would have to do is trace out the path of the word that you wanted to type in front of your camera, and your word would get keyed in for you. You can think of air typing as a mid-air version of swipe typing that you find on modern smartphone keyboards. Now, in order to build our models, we first had to correct a data set. In order to correct the data set, we used Google's MediaPipe library that provides lightweight real-time models for hand detection and pose estimation. The hand detection subpackage of MediaPipe provides us with 21 landmarks of hand positions. We use landmark number 8, which is the tip of the index finger, as our cursor. And we use the positions of the index fingertip across the input video to generate a trail of the input word. Using this pipeline, we create a dataset of image label pairs for image classification and image character sequence pairs for our image-to-sequence model. Every image is a static representation of a finger trail that was drawn in midair and captured by our laptop's camera. It's important to note that while generating finger trails, we use color to encode the temporal nature of finger movement. Using color is essential to discriminate words that have identical trail shapes, but which have different start points and end points. For example, the words not and ton have exactly the same finger trail shape and image, but due to the color gradient, we can tell that they are actually two different words. Using this methodology, we create a data set that was derived from the lyrics of Taylor Swift's song, Shake It Off. We chose the song as its lexicon is composed of 101 unique words, almost all of which occur in daily life scenarios. We collect 6 images per word for training, having a dataset of 600 training examples, and a further 300 images for testing, which we use to measure the performance of our models. Coming to our models, the first model that we implemented was an image classification model. This model classified every image of a finger trail into one of the 101 different words present in the lexicon of our dataset. We built this model upon MobileNet v2, which is a lightweight, low latency, and high accuracy image classification model. We implemented this model using PyTorch's Torch Vision package and fine-tuned it on our dataset for 1000 epochs. Again, since this model is an image classification model, it performs transcription at a word level and cannot handle unseen examples or character sequences that weren't in the input lexicon. In order to circumvent that limitation, we developed the second model, which is the image-to-sequence model.
The image-to-sequence model is designed to predict character sequences instead of word labels, therefore enabling prediction of out-of-dictionary words. Swipe typing is inherently a sequential process. While we move across the characters of words, the next word can theoretically be predicted using the previous stop location, movement vector, and halt times of the trail of the emphasized characters. And this is what we try to encode within the model as well. We derive inspiration from image captioning models that similarly take in an image and generate a sequence of words. We differ as Swiper predicts character sequences as opposed to word sequences. Additionally, the two differ as the Swiper dataset is a lot more structured compared to those used in image captioning models, thus allowing for simpler decoding methodologies. The image-to-sequence model builds upon the image classification model as an image encoder that generates 64-dimensional embeddings of the trail image and adds an autoregressive decoder to enable character-level inference. Each decoder timestep consists of a LSTM cell and a linear layer. At every timestep, we pass the image embedding, the hidden state and cell state from the previous timestep into the LSTM cell. The LSTM output is then passed through a linear layer to obtain the predicted character. For decoding, we experiment with providing both the embedding of the previous text output as well as the encoded image vector. We will later discuss our decision to stick to the image embedding as input to every decoding timestep. While the model converges during training, the model is not able to generalize the decoding mechanism for word strokes that show a deviation from the training set. The model performs well on decoding character sequences that follow similar swipe patterns of cadence, spline paths, and character halt times as that in the training set. However, any change in these characteristics during inference results in incorrectly classifying the first token, which further affects the decoding of the subsequent characters. However, additional diverse datasets should mitigate these effects. Let's now look at the results obtained on these models.
Coming to the results, our image classification model yielded an image classification accuracy of 87%, while the image-to-sequence model yielded a character error rate of 40%, where the character error rate measures the distance between the predicted and the reference characters. These numbers led us to conclude that for constrained lexicons, small vocabularies, and small datasets like ours, image classification appears to be a better approach than image-to-sequence modeling.
Let's now look at a demo of the application to assess its real-life feasibility. In this example, we try to input the sequence "My ex-man bought his new" using air typing. The lightweight pose estimation and classification model make the inference practically instantaneous, ensuring that the experience is as smooth as possible. We also incorporated a couple of gestures to start and stop trail generation, run inference, as well as clear the text output. In this example, we can see that the model classifies most of the words correctly and has a minimal error rate. Here we will discuss the issues that arose primarily due to limitations in the dataset. Let's first look at the perils of teacher forcing. During training, the decoder output at timestep t was initially conditioned on image embedding and ground truth character at timestep t-1. While this model trains fastest, converging in just around 350 epochs, it also yields the highest average character error rate of 99%. The model seemingly relied less on the context of the previous timestep and more on the ground truth character embedding fed during training. Teacher forcing results in poor predictive performance since the conditioning context that the decoder receives during inference diverges from the context encountered during training. To mitigate this limitation, we implemented beam search to generate the best joint predictions over all characters rather than per character best. However, decoding using beam search took an impractical amount of time. Therefore, the flaws of the limited dataset as well as the non-viable beam search method required us to forego the teacher forcing approach completely. Let's now look at the benefits of using image embedding versus the previous character. To mitigate the poor predictive performance of teacher forcing caused by the inability of the model to learn context, we instead opted to use the previous decoded output during training. The model took a lot longer to converge, but only had a marginal improvement in the character error rate of 95% as compared to 99% in the teacher forcing model. While it sporadically predicted words with complete accuracy, it was unable to adjust to variations in gestures. It had now learned a narrow language model due to the limited dataset and ignored the image context beyond the first few time steps. This prevented prediction of out-of-dictionary words. We now replace the previous decoder output text embedding with the image embedding of the encoder. This led to a significant improvement in character error rate, which now dropped to 39%. We theorized that providing each time step of the LSTM cell with the encoded image context, along with the language context from cell state and hidden state, would be sufficient to predict the next character label. The modification creates a moderating effect between the overpowering language modeling effects of the limited dataset by restricting explicit access to the previous character label and also enforcing the encoded image context at every time step. To conclude, Swiper provides a cohesive system for air typing without sophisticated hardware or sensors. the project required us to build proprietary workflows and manually create datasets drawn from the lexicon of Taylor Swift's Shake It Off. We then proposed two deep learning architectures to convert static finger trails into words. The first is a classification model that transcribes text at a word level, and the second is a sequence generation model that transcribes at a character level. We also discussed the benefits of one over the other, provided the dataset limitations, and finally developed an intuitive graphical user interface for users to interact with our models. In the future, we would like to expand our dataset to include more words and character sequences and also explore the use of transformers for better character-level transcription performance.